somewhere past the orbit of Neptune, roughly 4 billion miles from the place where you were born, the Sun becomes just another star, bright, yes, but no longer the center of anything, no longer warmth, no longer home. This is the edge of what we might call familiar, the boundary where the solar wind falters and the deep silence of interstellar space begins to press inward. To travel beyond this point, to drift outward into the true emptiness between stars, is to enter a kind of solitude that no human mind has ever known, a distance so vast that even light, patient, tireless light, would take years to carry a single word back to anyone who might be listening. If these quiet journeys through space help ease the mind toward rest, the subscribe button is always there, a small way to return. And now, with the stars waiting, we begin. On the 14th of February, 1990, a small spacecraft that had been traveling outward from Earth for nearly 13 years received an unusual instruction from the people who had built it, an instruction that had nothing to do with its scientific mission and everything to do with something quieter, something more human in nature. The spacecraft was Voyager 1. And by that Valentine's Day it had reached a distance of approximately 3.7 billion miles from the place where it had begun its journey, a distance so vast that the radio signals carrying that instruction had taken more than 5 hours to reach it, traveling at the speed of light across the darkness. The instruction was simple, though it required the spacecraft to do something it had not been designed to do. To turn its camera around and look back toward home, toward the inner solar system where the small rocky world of its origin was still circling the same yellow star it had always circled. This request had come from Carl Sagan, the astronomer and writer who had spent much of his life thinking about our place in the universe, and who understood that sometimes the most important thing a scientific instrument can do is show us something we already know but have never truly seen. The image that Voyager captured that day has come to be known as the pale blue, and if you have ever seen it, you will understand why it has stayed with so many people in the years since. The photograph shows almost nothing at all, in the conventional sense. Just bands of scattered light caused by the sun's rays catching the camera's optics, and within one of those bands, a tiny point of color so small that you might miss it entirely if you did not know to look. That point, that single pixel of soft blue suspended in a sunbeam, was Earth, was everything, was the whole of human history and every person who had ever lived and every story that had ever been told, reduced to a mote of dust floating in the vastness of space. Sagan wrote about this image with great tenderness, observing that everyone you have ever heard of, every human being who ever was, lived out their lives on this small speck. And there is something in his words that feels less like science and more like a lullaby, a gentle reminder that we are all here together on this fragile little world. It is this image, perhaps more than any other, that invites us to think about what it means to be alone in the universe. And yet the curious thing is that the image itself argues against loneliness, showing us a world that contains multitudes, a world where even at a distance of billions of miles, we remain connected to one another by the simple fact of sharing the same small home. The question of cosmic isolation is not a new one, of course, and people have been wondering about it for as long as we have looked up at the night sky and noticed how very many stars there are and how very far apart they seem to be. But the question takes on a different quality when you begin to travel outward, when you leave that pale blue dot behind and venture into the darkness between worlds. 21 years before Voyager took its famous photograph, on the 20th of July, 1969, a man named Michael Collins found himself in a position that no human being had ever occupied before, a position of such profound solitude that it is difficult for those of us who have always lived on Earth to fully comprehend. Collins was the command module pilot for the Apollo 11 mission, the mission that carried Neil Armstrong and Buzz Aldrin to the surface of the Moon. And while his two crewmates descended to the lunar surface in the landing module called Eagle, Collins remained alone in the command module Columbia, orbiting the Moon at an altitude of approximately 60 miles and a speed of around 3,600 miles per hour. When Columbia passed behind the Moon, as it did every 2 hours or so, the bulk of the lunar surface blocked all radio communication with Earth, and in those moments Collins was cut off from every other human being in existence, separated from Armstrong and Aldrin on the surface below by the width of the Moon itself, and separated from the 3 billion people on Earth by the vast gulf of space that lay between the Moon and home. The distance from Collins to his nearest fellow humans during those periods of isolation was approximately 2,235 miles, which might not sound like very much when compared to the billions of miles that Voyager would eventually travel. But distance alone does not capture the quality of his solitude. There was no possibility of rescue, no way for anyone to reach him if something went wrong, and the psychological weight of that knowledge must have been considerable, though Collins himself spoke of it with remarkable equanimity in the years that followed. He later described a feeling not of loneliness but of awareness, a heightened sense of where he was and what he was doing, and he noted that he did not feel frightened or abandoned but rather connected to something larger than himself, part of a great human endeavor that stretched back through all the engineers and scientists and dreamers who had made his journey possible. This is an important observation, and one that we will return to again as we consider what it truly means to be alone. The idea that physical isolation does not necessarily produce emotional isolation, and that connection can persist across distances that would seem to make it impossible. 8 years after Collins orbited the Moon in solitude, in the late summer of 1977, 2 spacecraft were launched from Cape Canaveral that would eventually travel farther from Earth than any human-made objects had ever traveled before. Voyager 2 lifted off on the 20th of August, and Voyager 1 followed on the 5th of September. And though their primary mission was to study the outer planets of our solar system, they carried with them something that had nothing to do with science in the traditional sense, something intended not for the worlds they would visit but for any beings who might find them in the distant future, long after they had left our solar system behind. Attached to each spacecraft was a golden phonograph record, 12 inches in diameter and plated in gold to protect it from the erosive effects of interstellar space, containing sounds and images that had been selected to represent the diversity of life and culture on Earth. The Golden Record, as it came to be known, was the product of a committee chaired by Carl Sagan, and its contents were chosen with great care over the course of several months, a process that required the committee to consider what they would want to say to any intelligence that might find these small emissaries in the depths of space. The record contains greetings in 55 human languages, from ancient Sumerian to modern Mandarin, as well as the songs of humpback whales and the sounds of wind and rain and thunder, and music ranging from Bach to Chuck Berry to traditional songs from cultures all around the world. There are 116 images encoded on the record, showing everything from the structure of DNA to the nursing of an infant to the architecture of the Taj Mahal. And there is a message from the Secretary General of the United Nations and a message from the President of the United States. And there are the brainwaves of a young woman named Andrew Yang, who would later become Carl Sagan's wife, recorded as she thought about what it means to be human and to love and to wonder about the cosmos. The chances that any extraterrestrial intelligence will ever find either of the Voyager spacecraft are, by any reasonable assessment, extraordinarily small, so small as to be almost negligible, and the people who created the golden record understood this perfectly well. The record was never really intended for aliens, or at least not primarily for aliens, but rather for us, for the people of Earth, as a reminder that we are capable of imagining contact with other minds even across the unimaginable distances of space, and that this act of imagination is itself a form of reaching out, a way of asserting that we are here and that we hope we are not alone. The record is an artifact of longing, a message in a bottle cast into an ocean so vast that the bottle may drift forever without ever washing up on any shore. And yet the casting of it was not an act of despair but an act of hope, a statement of faith that connection is possible even when the odds against it seem insurmountable. The question of whether we are alone in the universe had been asked in a more systematic way nearly 2 decades before the Voyager launches. In the spring of 1960, when a young astronomer named Frank Drake pointed a radio telescope at the sky and listened for signals that might indicate the presence of intelligent life elsewhere in the cosmos. Drake was working at the Green Bank Observatory in the mountains of West Virginia, a facility that had been established just a few years earlier and that would go on to become one of the most important centers for radio astronomy in the world. And his project was called Ozma, named after the princess in the Ounce books by L. Frank Baum, a name chosen because Ounce was a land far away, difficult to reach, and populated by strange and exotic beings. Project Ozma was modest in scope, lasting only a few months and focusing on just 2 nearby stars, Tau Ceti and Epsilon Eridani, both of which were similar to our own Sun and located at distances of approximately 11 and 10 light-years respectively, which made them among the closest stars that might plausibly host planets capable of supporting life. Drake and his colleagues listened for signals at a frequency of approximately 1420 MHz, a frequency chosen because it corresponds to the natural emission of hydrogen atoms, the most abundant element in the universe, and therefore a frequency that any technically advanced civilization might be expected to monitor. They heard nothing, of course. Or rather, they heard nothing that could be distinguished from the natural radio noise of the cosmos. But the project established the basic methodology for what would come to be known as the Search for Extraterrestrial Intelligence, or SETI, and Drake himself would go on to become one of the most important figures in that field, devoting much of his career to the question of whether we are alone. The curious thing about this question, the question of cosmic loneliness, is that for most of human history we have assumed we knew the answer. We have assumed that space is empty, that the stars are far away and the darkness between them is absolute, and that any journey outward from Earth would be a journey into ever-deepening isolation. The astronauts who traveled to the Moon understood this, and the people who built the Voyager spacecraft understood it, and the scientists who have searched for radio signals from other civilizations understand it too. And yet the more we learn about the universe, the less certain this assumption becomes. We now know that planets are common, that nearly every star in the sky has at least one world orbiting it, and that many of these worlds are similar in size and temperature to Earth. We know that the chemistry of life is not exotic or unusual, that the elements from which we are made are among the most abundant in the cosmos, and that the conditions necessary for life to arise may be far less restrictive than we once believed. And yet even if we are not alone in the universe, even if there are other minds out there looking up at their own night skies and wondering the same things we wonder, the distances involved are so vast that any communication between us would be measured not in minutes or hours but in years or centuries or millennia. The nearest star to our Sun is Proxima Centauri, just over 4 light-years away, which means that a radio signal sent from Earth would take more than 4 years to reach it. And any reply would take another 4 years to return. And that is for the nearest star. While most of the stars in our galaxy are thousands or tens of thousands of light-years distant. This brings us to a paradox that lies at the heart of the question we are exploring. The question of when and where and how a human being traveling outward from Earth would become truly alone. We have always assumed that space means isolation, that to leave our planet is to leave behind the web of connections that makes us human. And yet the astronauts who have actually made that journey report something quite different, something unexpected and profound. They speak of a phenomenon called the overview effect, a cognitive shift that occurs when you see the Earth from space for the first time. A shift that produces not a feeling of separation but a feeling of intense connection. An awareness of the planet as a single integrated system and of humanity as a single family sharing that fragile home. Edgar Mitchell, who walked on the Moon during the Apollo 14 mission in February of 1971, described this experience in terms that verge on the mystical, speaking of a sense of universal connectedness and an intuitive understanding that the molecules of his body and of his spacecraft and of his crewmates had all been manufactured in ancient stars, that we are all made of star stuff, as Carl Sagan would later put it, and that this shared origin binds us together in ways that distance cannot diminish. Other astronauts have described similar experiences. A profound sense of the unity of all life and a recognition that the boundaries we draw between ourselves and others, between our nation and other nations, between our species and other species, are in some fundamental sense illusory, that we are all part of something larger and older and more beautiful than we can easily comprehend from down here on the surface. This is not to say that space travel does not involve real risks and real hardships, or that the psychological challenges of long-duration missions are not significant, because they are, and we will explore them in detail as we continue our journey outward. But it does suggest that the question of cosmic loneliness is more complicated than it might first appear. That the relationship between physical distance and emotional isolation is not straightforward, and that the human capacity for connection may be more resilient than we have given it credit for. The pale blue dot that Voyager photographed from the edge of the solar system is impossibly tiny, a single pixel in an image dominated by darkness. And yet it contains within it every sunset you have ever watched and every friend you have ever known and every song you have ever loved. And that connection does not disappear simply because you have traveled far enough away to see it all at once. The question we are asking, then, is not really about fear, not about the terror of emptiness or the horror of being abandoned in the void. It is about wonder. About the strange and beautiful fact that we find ourselves here at all, on this small world orbiting an ordinary star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. It is about the even stranger fact that we are capable of asking these questions, of building spacecraft and sending them outward, of encoding our music and our images on golden records and casting them into the darkness in the hope that someday, somewhere, someone might find them and know that we existed. And it is about the question that nobody thought to ask until we had actually begun to travel into space and discovered that the answer was not at all what we expected. The question of when, exactly, a human being traveling outward from Earth would cross some invisible threshold and become, for the first time, truly and completely alone. When we begin to consider how far a human might travel from Earth before finding themselves truly alone, it helps to start by looking around at what already surrounds us, at the surprisingly crowded neighborhood that exists in the space immediately above our heads and extending outward in all directions. A neighborhood that turns out to be far busier, far more populated with objects both natural and human-made than most of us ever pause to consider when we look up at the night sky and see only darkness punctuated by distant points of light. If you were to rise slowly from the surface of the Earth, passing through the thin blue envelope of atmosphere that keeps us all alive, you would not find yourself immediately alone, not by any measure, because the space just above our planet has become, over the past several decades, a rather cluttered place, filled with the accumulated machinery of human ambition and curiosity and communication, all of it circling the Earth in patient orbits, some moving faster than others, some climbing higher, some skimming just above the outermost wisps of atmosphere, but all of them together forming a kind of mechanical swarm that we have placed there piece by piece since the first satellite, Sputnik, beeped its way into orbit in 1957. As of 2024, there are more than 5,000 active satellites circling our planet, 5,000 separate machines that are currently functioning, receiving signals and transmitting signals and taking photographs and measuring temperatures and tracking weather patterns and enabling the quiet miracle of a message sent from one side of the world to the other in less than a second. And this number of 5,000 represents only the satellites that are still working, still responding to commands, still performing the tasks for which they were designed. And it does not include the far greater number of objects that are no longer active but remain in orbit nonetheless, tumbling and drifting along the paths they were placed in years or decades ago. Among these 5,000 active satellites, there is one that holds a particular significance, one structure that has been continuously occupied by human beings since November of the year 2000. Which means that for nearly a quarter of a century now, there has not been a single moment when all of humanity was gathered together on the surface of the Earth, because some of us have always been up there, living and working and sleeping and eating and looking down at the planet through small round windows. And this structure is the International Space Station, which orbits at an altitude of approximately 254 miles above the surface, completing one full circuit of the Earth roughly every 90 minutes, moving at a speed of about 17,500 miles per hour, though from inside it feels perfectly still, just as a passenger on a smoothly flying airplane might forget they are moving at all. The International Space Station is not the first space station we have built, nor is it likely to be the last. But it represents something quietly remarkable, a place where humans have maintained a continuous presence in space, taking turns, rotating crews, for more than 23 years without interruption, and during all that time the station has been our farthest permanent outpost, the place where humanity ends and the rest of the cosmos begins, though of course it is not very far at all by cosmic standards, being only 254 miles up, which is to say that if you could drive a car straight upward at highway speeds, you would arrive at the station in perhaps 4 or 5 hours, a distance shorter than many people commute to work over the course of a week. But the station is not alone up there, and neither are the 5,000 working satellites, because space, it turns out, has become littered with the remnants of our previous activities, the spent rocket stages and defunct satellites and fragments of collisions and the accumulated debris of 6 to 7 years of space exploration. And NASA, which tracks all of this material very carefully for the safety of astronauts and functioning spacecraft, currently monitors more than 27,000 objects larger than 10 centimeters in diameter, which is to say larger than roughly the size of a softball, all of them orbiting the Earth at tremendous speeds. And while 27,000 may not sound like very many objects spread across the vast emptiness of near-Earth space, they are traveling so fast that even a small piece of debris can cause tremendous damage. And so the space around our planet is not empty at all, but rather requires careful navigation. A kind of cosmic traffic management that goes on quietly every day without most of us ever being aware of it. Beyond this crowded shell of satellites and debris, extending outward into the darkness, we find our nearest cosmic neighbor, the Moon, which orbits the Earth at an average distance of 238,855 miles. Though this distance varies somewhat as the Moon follows its slightly elliptical path, sometimes drawing closer and sometimes drifting farther away. And this distance of nearly 250,000 miles might sound very far indeed. And it is far compared to anything we experience in our daily lives on the surface of the Earth. But it is also close enough that light from a flashlight shone toward the Moon, if such a beam could somehow maintain its coherence, would arrive there in just over 1 second. And radio signals travel at the same speed, which means that when we communicate with spacecraft on or near the Moon, there is only a brief delay, just long enough to notice, between sending a message and receiving a reply. The Moon is the only celestial body beyond Earth where human beings have ever stood, where human boots have pressed into the fine grey dust and left footprints that remain there still, undisturbed by wind or rain, because there is no wind and no rain on the Moon. And between the years 1969 and 1972, 12 human beings walked on its surface, 12 people out of all the billions who have ever lived. And since December of 1972, when the astronauts of Apollo 17 lifted off from the lunar surface and began their journey home, no human being has traveled farther from Earth than the low orbit of the International Space Station, which means that for more than 50 years now, the Moon has remained the high-water mark of human exploration, the farthest place where any of us have ever been. Continuing outward from the Moon, we encounter a series of special locations in space known as Lagrange points, which are positions where the gravitational pull of the Earth and the gravitational pull of the Sun balance in such a way that a spacecraft can remain relatively stationary with respect to both bodies, requiring only small amounts of fuel to maintain its position. And there are 5 of these points in the Earth-Sun system, labeled simply with the letter L and the numbers 1 through 5. And each of them has different properties that make it useful for different purposes. But one of them, the point designated L2, has become particularly important in recent years because it is where we have placed some of our most sophisticated observatories, instruments designed to look outward into the universe and gather light from the most distant stars and galaxies. The James Webb Space Telescope, which was launched in December of 2021 after decades of development and anticipation, now resides at this L2 point, approximately 1 million miles from Earth, drifting along in a gentle orbit around this invisible balance point while it peers into the infrared spectrum and captures images of objects so far away that their light has been traveling toward us for billions of years. And at this distance of 1 million miles, the telescope is far enough from Earth to escape most of the heat and light that our planet radiates, which would otherwise interfere with its sensitive instruments. But it is still close enough to maintain constant communication with the scientists who operate it, still close enough to be, in some sense, part of our immediate neighborhood, a distant outpost perhaps, but one that remains firmly connected to home. Expanding our view still further, we must consider the influence of the Sun itself, which dominates our local region of space not only through its gravitational pull, but also through the constant stream of charged particles it sends outward in all directions, a flow known as the solar wind. And this wind creates a vast bubble in the interstellar medium, pushing back against the thin gas that fills the space between stars. And this bubble is called the heliosphere, and it extends outward from the Sun to a distance of roughly 11 billion miles. Though this boundary is not a sharp line but rather a gradual transition zone where the solar wind slows and eventually merges with the interstellar medium. And everything within this bubble, including our Earth and all the other planets and all the asteroids and comets and spacecraft we have ever launched, exists within the protective embrace of our star, sheltered to some degree from the harsher environment of interstellar space. Only a few of our spacecraft have ever approached the edge of this bubble, and only 2 have clearly passed beyond it into interstellar space. And one of these is Pioneer 10, a small probe launched in March of 1972, which was the first spacecraft to pass through the asteroid belt, the first to fly by Jupiter and return close-up images of that giant planet, and which has now been traveling outward from the Sun for more than 52 years. Its radio transmitter long since fallen silent due to the decay of its power source, but its physical form still coasting onward through the darkness at a speed of roughly 27,000 miles per hour. And as of recent calculations, Pioneer 10 is now approximately 12.3 billion miles from the Sun, which is to say that it has passed beyond the heliosphere and entered the true interstellar space between the stars. And it will continue traveling in that direction, gradually slowing due to the faint gravitational pull of the Sun but never quite stopping, never returning, carrying with it a small plaque depicting a man and a woman and the location of our solar system, a message in a bottle thrown into an ocean of unimaginable size. Closer to home, within the inner solar system where Earth makes its yearly journey around the Sun, we find ourselves accompanied by a surprising number of rocky companions, asteroids, and small bodies that orbit nearby, sometimes crossing our path, sometimes approaching close enough to be studied by our telescopes. And these near-Earth asteroids, as they are called, have been the subject of increasing attention in recent decades, both because some of them pose a potential threat to our planet if their orbits should someday intersect with ours at the wrong moment, and because others represent possible destinations for future exploration or even resource extraction. And as of recent counts, more than 32,000 of these near-Earth asteroids have been discovered. 32,000 rocky bodies ranging in size from small boulders to objects several kilometers across, all of them sharing our general region of the solar system, all of them reminding us that space, even the space near Earth, is not the empty void we might imagine but rather a place with its own geography and its own population of objects, some of which we have only recently begun to notice and catalogue. And finally, extending outward in a different way, not as physical objects but as waves of electromagnetic energy, we must consider the radio signals that humanity has been broadcasting into space since the early 20th century, since the first radio transmissions began to escape our atmosphere and travel outward at the speed of light in all directions. And these signals, growing weaker with distance but never quite disappearing entirely, have now been traveling for more than a century, which means that they have expanded outward to form a bubble roughly 200 light-years in diameter, a sphere of human presence, of human noise, that encompasses thousands of nearby stars and whatever planets might orbit them. And while these signals are almost certainly too faint to be detected by any technology we can imagine at such distances, they nonetheless represent a kind of announcement, a declaration that we are here, that Earth is inhabited by a species that builds transmitters and sends signals into the void. And this expanding bubble of radio noise makes our neighborhood larger than we might have thought, not in terms of what we have physically touched or visited, but in terms of what we have influenced, what we have reached out toward, even if only with the faintest of whispers. The neighborhood, it turns out, is busier than we imagine, crowded with satellites and debris, visited by 12 brave souls who walked on the moon and returned to tell of it, watched over by telescopes a million miles away, bounded by the great bubble of the heliosphere 11 billion miles distant, populated by tens of thousands of asteroids we are still learning to name and track, and announced to the cosmos by an ever-expanding sphere of radio waves that has been growing since before any of us were born. And all of this crowded and complicated and busy region of space, represents merely the beginning of our journey outward, merely the first steps into a universe that extends far, far beyond anything we have yet explored. But for now, as we settle in and let our thoughts drift gently towards sleep, it is enough to know that the space around Earth is not empty, that we are surrounded by the evidence of our own curiosity and ambition, and that the journey toward true solitude, toward being genuinely and completely alone in the cosmos, would require traveling much farther than most of us have ever considered. Let us begin this part of our journey by standing, in our imagination, on the surface of the moon. This is not so very far from home, as cosmic distances go. The moon orbits our planet at an average distance of about 239,000 miles, which is roughly the distance you might travel if you drove around the Earth at the equator nearly 10 times. From this vantage point, which 12 human beings have actually occupied during the Apollo missions between 1969 and 1972, the Earth appears as a stunning sphere suspended in the blackness of space. It fills a portion of the sky roughly 4 times larger than the moon appears to us when we gaze upward from our gardens or bedroom windows on a clear evening. The blue of the oceans, the white swirl of cloud systems, the brown and green patches of continents, all of these are clearly visible to the unaided eye. From the moon, you would never feel truly far from home. Earth hangs there, luminous and welcoming, a constant companion in the lunar sky, and you might find it rather comforting to know that everything you have ever known, every person you have ever met, every meal you have ever eaten, exists on that glowing sphere just a 3-day journey away. But let us now drift outward, gently and gradually, as we consider what happens to the appearance of our home world as the distance between us and it begins to grow. When we reach the orbit of Mars, the change becomes quite pronounced, though perhaps not in the way you might initially expect. Mars, our neighboring planet with its rusty red surface and thin carbon dioxide atmosphere, varies considerably in its distance from Earth depending on where both planets happen to be in their respective orbits around the Sun. At its closest approach, which astronomers call opposition, Mars comes within about 33.9 million miles of Earth. At its most distant, when Mars and Earth are on opposite sides of the Sun, that distance stretches to roughly 250 million miles. Let us consider the closer distance for now, that 33.9 million miles, which is still approximately 142 times farther than the Moon. From Mars, the Earth no longer appears as a detailed world with visible features. Instead, it has become what we might call a bright evening star, or perhaps a morning star, depending on the geometry of the planets at any given time. It shines with a steady blue-white light against the Martian sky, which itself takes on a butterscotch or salmon-pink color during the day due to fine dust particles suspended in that thin atmosphere. On the 14th of February in 2014, the Curiosity rover, which had landed on Mars in August of 2012, turned its cameras toward the evening sky and captured a photograph of Earth as seen from the surface of another world. In that image, our planet appears as a small bright point of light, hovering above the Martian horizon just after sunset. If you look very carefully at the original image, you can actually make out a tiny companion point of light very close to Earth, and this is the Moon, visible as a separate object despite the vast distance. The photograph is rather moving in its simplicity. There is the rocky Martian terrain in the foreground. There is the dusty sky fading from light to dark. And there, suspended in the heavens, is everything you have ever known reduced to a pinprick of light. Yet still, from Mars, Earth remains one of the brightest objects in the night sky, easily found and observed, a reliable beacon that connects you, however tenuously, to home. Now we must discuss a principle that governs how light behaves as it travels across space, and this principle, known as the inverse square law, will help us understand why the light of home grows dim in such a predictable manner. The inverse square law tells us that the intensity of light, or indeed any radiation spreading outward from a source, decreases in proportion to the square of the distance from that source. This means that if you double your distance from a light source, the light you receive is not merely half as bright, but 1/4 as bright. If you triple your distance, the light becomes 1/9 as intense. If you move 10 times farther away, the light is 1/100th as strong. This mathematical relationship applies to all electromagnetic radiation, including the visible light reflected from Earth's surface and atmosphere, the radio signals we broadcast into space, and the thermal radiation emitted by any warm object. The law arises from a simple geometric fact, which is that light spreads outward in all directions from its source, and as it travels farther, it must cover an ever larger spherical surface area. Since that surface area grows with the square of the radius, the energy passing through any given patch of that surface diminishes accordingly. The inverse square law is both beautiful in its simplicity and rather humbling in its implications, for it means that the presence of home fades not gradually but with increasing rapidity as you venture outward into the dark. Let us now leap outward to one of the most remarkable perspectives ever captured, the famous pale blue dot image taken by the Voyager 1 spacecraft on the 14th of February 1990. Voyager 1 had been launched from Cape Canaveral on the 5th of September 1977, and by February of 1990, it had traveled to a distance of approximately 6 billion kilometers, or about 40 astronomical units, from the Sun. An astronomical unit, you may recall, is the average distance between the Earth and the Sun, roughly 93 million miles or 150 million kilometers. At the request of the astronomer Carl Sagan, the spacecraft was commanded to turn its camera back toward the inner solar system and capture a series of images that would come to be known as the family portrait. One of those images included Earth, and when the photograph was processed, our planet appeared as a tiny pale blue speck suspended in a band of scattered light from the Sun. The Earth occupied less than a single pixel in that image, and yet it remained just barely visible, a faint point of color against the infinite blackness. The light required approximately 5.5 hours to travel from Earth to the spacecraft's position, and the signal carrying that image back to Earth required the same duration to return. At such a distance, the inverse square law had reduced the light reflected from Earth to something almost imperceptible, and yet still, Voyager 1 could detect it. The image reminds us that our planet, which feels so solid and vast beneath our feet, is in truth a rather small and fragile world, and that everything we know and love exists upon that single mote of dust suspended in a sunbeam. We should now consider another spacecraft that continues its journey outward even as we speak. New Horizons was launched from Earth on the 19th of January 2006. And it carried with it a suite of instruments designed to study Pluto and the outer solar system. On the 14th of July 2015, After a journey of more than 9 years, New Horizons conducted a close flyby of Pluto, returning the first detailed images of that distant dwarf planet's surface. Since then, the spacecraft has continued onward into the Kuiper Belt, that vast ring of icy bodies that extends from roughly the orbit of Neptune outward for several billion kilometers. New Horizons passed by a small Kuiper Belt object named Arrokoth on the 1st of January 2019, and it continues to send back data about the environment in this distant region. From the current position of New Horizons, the Sun has shrunk to a very bright star, far outshining all others but no longer appearing as the brilliant disk we know from Earth. Our home planet, from that vantage, would be virtually impossible to detect with the naked eye, lost in the glare of the Sun and reduced by distance to something far fainter than the faintest star visible from a dark mountain top on Earth. And now we come to a boundary that Voyager 1 crossed in August of 2012, a threshold known as the heliopause. To understand the heliopause, we must first understand that the Sun emits a continuous stream of charged particles, mostly protons and electrons, that flow outward in all directions at speeds ranging from 300 to 800 kilometers per second. This stream is called the solar wind, and it creates a vast bubble around our solar system known as the heliosphere. The heliosphere extends outward until the pressure of the solar wind is balanced by the pressure of the interstellar medium, which is the thin gas and dust that fills the space between stars in our galaxy. The boundary where this balance occurs is the heliopause, and beyond it lies true interstellar space, the realm between the stars. Scientists at the Jet Propulsion Laboratory were able to confirm that Voyager 1 had crossed this boundary by analyzing plasma oscillation data collected by the spacecraft's instruments. When certain solar events caused disturbances to propagate outward through space, the spacecraft detected oscillations in the plasma surrounding it, and the frequency of these oscillations indicated a much higher density of charged particles than would be found within the heliosphere. This confirmed that Voyager 1 had indeed entered interstellar space, becoming the first human-made object to do so. It is worth pausing to appreciate that even at this distance, roughly 121 astronomical units or about 18 billion kilometers from the Sun, Voyager 1 remains in radio contact with Earth. The signals are extraordinarily faint, requiring dishes 70 meters across to detect, but they still arrive, carrying data about the environment at the very edge of our solar neighborhood. Beyond the heliopause lies an even vaster region that remains largely theoretical, known as the Oort cloud. The Dutch astronomer Jan Hendrik Oort proposed the existence of this structure in 1950, based on his analysis of the orbits of long-period comets. These comets, which take thousands or even millions of years to complete a single orbit around the Sun, seemed to originate from a spherical shell of icy bodies surrounding our solar system at enormous distances. Oort calculated that this cloud might extend from roughly 2,000 astronomical units to as far as 200,000 astronomical units, which translates to approximately 3 light-years or even slightly more. A light-year, you will recall, is the distance that light travels in 1 year, roughly 9.5 trillion kilometers or about 6 trillion miles. The Oort cloud, if it exists as Oort proposed, would contain trillions of icy bodies, remnants from the formation of the solar system that were gravitationally scattered outward by interactions with the giant planets billions of years ago. No spacecraft has yet traveled far enough to directly observe the Oort cloud, and at Voyager 1's current speed of roughly 17 kilometers per second, it would take approximately 300 years to reach the inner edge of this hypothetical structure, and perhaps 30,000 years to pass through it entirely. This brings us to a question of particular relevance to our gentle meditation on solitude, which is the matter of how far Earth's radio signals might travel before becoming indistinguishable from the cosmic background noise. Since the early 20th century, humanity has been broadcasting radio waves into space, first unintentionally as a byproduct of early radio and television transmissions, and later deliberately in the form of powerful radar signals and intentional messages to the stars. These signals travel outward at the speed of light, forming an ever-expanding bubble of electromagnetic evidence of our existence. However, the inverse square law applies to these radio waves just as it does to visible light, and as the signals spread outward, they become progressively weaker. There is also the matter of the cosmic microwave background, the faint glow of radiation left over from the early universe, as well as various natural radio sources such as pulsars and quasars that contribute to the background noise of the cosmos. Calculations by various researchers, taking into account the power of typical television broadcast towers and the sensitivity of radio telescopes comparable to those we have on Earth, suggest that our radio signature might become indistinguishable from cosmic background noise at a distance of approximately 1 to 2 light-years. More powerful, focus transmissions such as the Arecibo message sent in 1974 might be detectable at somewhat greater distances, perhaps tens of light-years, but only if a receiver happened to be located directly in the narrow beam of the transmission. Beyond roughly 2 light-years, then, a traveler might find that even the faintest whisper of human radio broadcasts had faded below the threshold of detectability, lost in the gentle hiss of the universe itself. And so we find ourselves contemplating a gradual transition, from the brilliant blue marble visible from the Moon, to the bright evening star seen from Mars, to the pale blue dot captured by Voyager 1, to the imperceptible mote that Earth would become from the Oort cloud, to the final fading of even our radio presence at 1 or 2 light-years from home. This progression is not sudden or dramatic but rather smooth and mathematical, governed by the simple and elegant inverse square law that treats all light and all radiation with perfect impartiality. The light of home grows dim not through any malice or intent, but simply because of the geometry of our universe, the way that energy must spread itself ever thinner across ever larger spheres of space. There is something rather peaceful in contemplating this gentle diminution, this slow dissolving of the familiar into the dark. Each stage of the journey outward brings a softer, more distant view of everything we know, until at last the light of home fades to nothing at all, and the traveler is left with only the stars and the endless quiet of interstellar space. When we look up at the night sky and see the stars scattered across that velvet darkness, it can feel as though we are gazing out into an infinite emptiness, a void so vast and so cold that the word loneliness does not quite capture its scale. But this impression, while understandable, is not entirely accurate, and in fact the reality of our cosmic situation is rather more comforting than it might at first appear. The space between the stars is not an unbroken ocean of nothingness stretching uniformly in all directions, but rather something more like an archipelago, a chain of islands rising from dark waters, each island separated from its neighbors by considerable distances, yes, but not by distances that are entirely beyond comprehension or entirely beyond the theoretical reach of future exploration. Our stellar neighborhood, when viewed from this perspective, begins to feel less like exile on an isolated rock in infinite blackness and more like residence on one particularly pleasant island in a scattered but navigable chain. The nearest of these neighboring islands, the closest star to our own sun, is a small and rather dim red dwarf called Proxima Centauri, and it sits at a distance of approximately 4.24 light-years from Earth. A light-year, as you may recall from earlier in our discussion, is the distance that light travels in 1 year through the vacuum of space, which works out to roughly 9.5 trillion kilometers, a figure so large that it loses meaning almost immediately upon hearing it. But Proxima Centauri, despite being this almost incomprehensible distance away, is genuinely close by cosmic standards, close enough that astronomers have studied it in considerable detail and close enough that it features prominently in discussions of where humanity might one day send its first interstellar probes. The star was discovered in 1915 by a Scottish astronomer named Robert Innes, who was working at the time at the Union Observatory in Johannesburg, South Africa. Innes was examining photographic plates of the southern sky, comparing images taken at different times to look for stars that had moved relative to the background of more distant objects, and in doing so he noticed a faint red star that shared the same motion through space as the bright star Alpha Centauri. This indicated that the two were gravitationally bound, traveling together through the galaxy, and Innes realized that this dim companion was actually slightly closer to us than Alpha Centauri itself, making it the nearest star to our solar system, a record it has held ever since. Proxima Centauri is not alone in that region of space, but rather forms part of a triple star system along with the two stars that make up Alpha Centauri proper. Alpha Centauri A and Alpha Centauri B are a binary pair, two stars orbiting around their common center of mass in a dance that takes approximately 80 years to complete. Alpha Centauri A is very similar to our own Sun, a yellow star of comparable size and temperature and luminosity, the sort of star around which one might expect to find worlds not entirely unlike Earth. Alpha Centauri B is somewhat smaller and cooler, an orange star that nonetheless puts out enough light and heat to warm any planets that might orbit at suitable distances. These two stars are separated from each other by distances that vary between roughly the distance from our Sun to Saturn and the distance from our Sun to Pluto, depending on where they are in their mutual orbit, and they present to telescopes on Earth as a single bright point of light, the third brightest star in our night sky. Proxima Centauri orbits much farther out, at a distance of about 13,000 astronomical units from the central pair, which means it takes more than 500,000 years to complete a single orbit. It is a small star, only about 12% of the Sun's mass, and it glows with a dim red light that is invisible to the naked eye despite its relative proximity to Earth. You could not step outside on a clear night and point to Proxima Centauri without the aid of a telescope, even though it is the nearest star beyond our own. Just slightly farther away, at a distance of approximately 6 light-years, we find another red dwarf known as Barnard's star, and this particular star has its own interesting story of discovery and study. In 1916, just 1 year after Innes found Proxima Centauri, an American astronomer named Edward Emerson Barnard was examining photographic plates of the northern sky and noticed something remarkable. There was a dim red star that had moved across the photographs by an unusually large amount between images, more than any other star Barnard had ever observed, and this high proper motion, as astronomers call it, indicated that the star was relatively close to the Sun and moving through space at a significant speed relative to our solar system. Barnard's star, as it came to be known, travels across our sky at a rate of about 10.3 arcseconds per year, which means that over the course of a human lifetime it moves by a distance roughly equal to half the width of the full moon. This is still too small to notice with the unaided eye, but it is extraordinarily fast by the standards of stellar motion, and it earned Barnard's star the distinction of having the largest proper motion of any known star. The star itself is ancient, perhaps 7 to 12 billion years old, and like Proxima Centauri it is a small red dwarf, putting out only a tiny fraction of the light that our Sun produces. The study of these nearest stars has accelerated dramatically in recent decades, driven in part by improvements in telescope technology and in part by the growing interest in finding planets beyond our solar system. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri, a world now known as Proxima Centauri b, and this discovery captured the imagination of scientists and the public alike because the planet appears to be located within its star's habitable zone, that region around a star where temperatures might allow liquid water to exist on a planetary surface. Proxima Centauri b is estimated to be at least 1.3 times the mass of Earth, which makes it a rocky world rather than a gas giant, and it orbits its parent star at a distance of only about 7.5 million kilometers, completing one orbit every 11.2 days. This seems extraordinarily close compared to the orbits of planets in our own solar system, but because Proxima Centauri is so much cooler and dimmer than our Sun, this close orbit actually places the planet in the zone where liquid water could theoretically exist. Whether Proxima Centauri b actually has water, or an atmosphere, or conditions suitable for life as we understand it, remains unknown, and red dwarf stars like Proxima Centauri are known to produce powerful flares of radiation that might strip away any atmosphere a close-orbiting planet possessed. But the mere existence of a roughly Earth-sized planet in the habitable zone of the nearest star to our Sun was a discovery of profound significance, a reminder that the archipelago of stars around us might contain islands that are not merely rocks in the void but potentially places where life could take hold. Even more remarkable, in some ways, was the discovery of the TRAPPIST-1 system, which lies approximately 40 light-years from Earth in the direction of the constellation Aquarius. In 2016 and 2017, astronomers using a relatively small telescope in Chile, a 60-centimeter instrument designed specifically to search for planets around dim red dwarf stars, found evidence of not one but 7 Earth-sized planets orbiting a single small star. The star itself, TRAPPIST-1, is an ultra-cool red dwarf only slightly larger than Jupiter, and it puts out so little light that all 7 of its known planets orbit closer to it than Mercury orbits our Sun. Yet because the star is so dim and cool, at least 3 and possibly more of these 7 worlds appear to lie within the habitable zone, making the TRAPPIST-1 system one of the most intriguing targets for the search for life beyond Earth. The discovery demonstrated that relatively modest telescopes, when pointed at the right targets and operated with sufficient patience, could reveal entire systems of potentially habitable worlds, and it suggested that the galaxy might be far richer in Earth-like planets than earlier generations of astronomers had dared to hope. Our knowledge of the stellar neighborhood has been transformed in recent years by the work of the Gaia Space Telescope, which was launched by the European Space Agency in 2013 and has been systematically mapping the positions and motions of stars across the entire sky. Gaia measures the positions of stars with extraordinary precision, accurate enough to detect the tiny wobbles that occur when a star shifts position as Earth moves around the Sun, and from these measurements astronomers can calculate the distances to stars with far greater accuracy than was previously possible. The telescope has now catalogued approximately 1.8 billion stars, measuring their positions, their distances, their colors, and their motions through space, and this vast data set has revolutionized our understanding of the structure and history of our galaxy. Among its many discoveries, Gaia has helped identify numerous nearby stars that had previously been overlooked, filling in the details of our local stellar neighborhood and revealing just how many islands of light exist within a few dozen light-years of our Sun. One of these nearby stars is Luton's star, a red dwarf located approximately 12.2 light-years from Earth in the constellation Canis Minor. The star was catalogued by the Dutch-American astronomer Willem Luton, who spent much of his career identifying stars with high proper motion, and in recent years it has attracted attention because of evidence that it hosts at least one planet orbiting within its habitable zone. This planet, sometimes called Luton B, appears to be a super-Earth, perhaps 2 to 3 times the mass of our own planet, and it receives about the same amount of energy from its star as Earth receives from the Sun. Like all planets around red dwarf stars, it faces the challenges of stellar flares and the possibility of being tidally locked, with one face perpetually turned toward its star and the other in eternal darkness. But it nonetheless represents another potential destination in the archipelago of worlds that surrounds us. And so we find ourselves not in an empty void but in a neighborhood, a collection of nearby stars that are separated from us by distances that are vast by everyday standards but manageable by the standards of cosmic geography. The nearest of these stars, Proxima Centauri, is a mere 4.24 light-years away. And while this distance is still enormous, it is not infinite, not beyond all hope of crossing. To put this distance in perspective, consider the spacecraft Voyager 1, which was launched in 1977 and has been traveling outward from Earth ever since, becoming the first human-made object to enter interstellar space. Voyager 1 moves at a speed of approximately 38,000 miles per hour, or about 17 kilometers per second, which is extraordinarily fast by the standards of human transportation but relatively slow by the standards of cosmic distances. At this speed, traveling in a straight line toward Proxima Centauri, Voyager 1 would require approximately 73,000 years to complete the journey. This is a very long time indeed, longer than all of recorded human history, longer than the time since our ancestors first painted images on cave walls. But it is not forever, not an infinite span, and it suggests that with sufficient patience, or with faster spacecraft, the gaps between the islands of our stellar archipelago might one day be crossed. And so we find ourselves ready to lift our gaze even higher, to consider not merely our solar system with its familiar planets and distant comets, but the vast and quietly magnificent structure that contains us all, the great spiral of stars and dust and empty space that we call the Milky Way, a name that comes from the ancient observation of that pale band of light stretching across the night sky, which our ancestors recognized long before they understood its true nature, and which we now know to be our edge-on view of a galaxy so immense that the numbers we use to describe it seem almost to lose their meaning, becoming instead a kind of poetry, a way of gesturing toward something too large for the human mind to truly grasp, and yet something that science has patiently measured and mapped and come to understand with remarkable precision over the past century of careful observation. The Milky Way, our home galaxy, contains somewhere between 100 billion and 400 billion stars, and this range might seem imprecise for such an important figure, but it reflects the genuine difficulty of counting objects in a system so vast that we cannot step outside it to take a proper census, and so must instead estimate from our position within one of its spiral arms, peering through veils of dust and across distances so great that light itself, the fastest thing in the universe, requires tens of thousands of years to cross from one side to the other. The estimated diameter of our galaxy is approximately 100,000 light-years, which means that if you were to send a signal at the speed of light from one edge of the Milky Way to the other, that signal would arrive at its destination 100,000 years later, by which time entire civilizations might have risen and fallen, ice ages might have come and gone, and the very stars themselves would have shifted noticeably in their positions relative to one another, drifting on their long orbits around the galactic center like leaves caught in an impossibly slow whirlpool. Within this vast structure, orbiting these hundreds of billions of stars, are planets, and for most of human history we had no way of knowing whether planets beyond our solar system even existed, whether the worlds circling our own sun were a cosmic rarity or a common feature of stellar systems throughout the galaxy. This question was answered decisively and beautifully by the Kepler Space Telescope, a spacecraft launched by NASA in March of 2009 with the specific mission of staring at a single patch of sky and watching for the tiny, regular dimming of starlight that would indicate a planet passing in front of its host star. Over the course of its mission, which continued until November of 2018 when the spacecraft finally exhausted its fuel supply, Kepler confirmed the existence of over 2,600 exoplanets, worlds orbiting other stars, each one a place with its own particular characteristics of size and temperature and orbital period. And this number represented only the planets detectable by Kepler's specific method within its relatively small field of view, suggesting that the true number of planets in our galaxy must be staggeringly, almost incomprehensibly large. Subsequent analysis of Kepler's data, combined with observations from other telescopes and missions, has led astronomers to conclude that on average there is at least one planet for every star in the Milky Way, and quite possibly more, meaning that our galaxy contains not merely hundreds of billions of stars but hundreds of billions of planetary systems, each one a potential site for the kinds of conditions that might support the emergence and development of life. More specifically, recent studies have suggested that approximately 1 in 5 Sun-like stars may have an Earth-like planet orbiting within its habitable zone, that region around a star where temperatures are suitable for liquid water to exist on a planetary surface. And this finding transforms our understanding of our cosmic neighborhood profoundly, suggesting that potentially habitable worlds are not rare exceptions but rather common features of the galactic landscape, scattered throughout the spiral arms like wildflowers in an immense and quiet meadow. The question of how many of these worlds might actually harbor life, and how many of those life-bearing worlds might have developed intelligent, technological civilizations capable of communication or travel across interstellar distances, was first addressed in a formal mathematical way by the astronomer Frank Drake in 1961. When he convened a small meeting at the Green Bank Observatory in West Virginia to discuss the possibility of detecting signals from extraterrestrial intelligence. For this meeting, Drake developed what has come to be known as the Drake equation, which is not really an equation in the sense of providing a definitive answer, but rather a framework for thinking about the problem. A way of breaking down the grand question of how many civilizations might exist into a series of smaller, potentially answerable questions about the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction of life-bearing planets that develop intelligence, and so on through several additional factors including the average lifetime of a technological civilization. Drake's original estimate, based on the limited knowledge available in 1961, suggested that there might be somewhere between 1,000 and 100 million technological civilizations in our galaxy, a range so wide as to be almost humorous in its uncertainty, and yet this was an honest reflection of how little we knew at the time about the various factors in the equation. In the decades since, our knowledge of some of these factors has improved dramatically, particularly our understanding of how common planets are and how frequently Earth-like conditions might occur, while other factors, such as the probability that life will emerge on a suitable planet or that intelligence will evolve once life has appeared, remain deeply uncertain. Modern calculations using updated estimates for the known factors suggest that there could potentially be millions of technological civilizations in the Milky Way, though such estimates necessarily involve significant speculation about the factors we cannot yet measure, and reasonable scientists can arrive at vastly different numbers depending on their assumptions about the likelihood of various biological and cultural developments. What we have learned with increasing certainty over the past few decades is that life on Earth is far more resilient and adaptable than we once imagined, capable of surviving and even thriving in conditions that would have been considered impossible for biology just a generation or two ago. The discovery of organisms known as extremophiles, creatures that live in extreme environments, has expanded our understanding of the range of conditions compatible with life and has suggested that the universe may offer many more potential homes for living things than we previously supposed. In the deepest parts of the Mariana Trench, nearly 11 kilometers below the surface of the Pacific Ocean, where the pressure is more than 1,000 times greater than at sea level and no sunlight has ever penetrated, bacteria and other microorganisms carry on their metabolic processes in perfect contentment, drawing energy from chemical reactions in the absence of any solar input whatsoever. Beneath the ice sheets of Antarctica, in subglacial lakes that have been sealed off from the surface for millions of years, living organisms have been discovered persisting in cold darkness, their existence a quiet testament to life's remarkable ability to find a way forward even in the most unpromising circumstances. Perhaps most remarkably, in 2007, during the Photon M3 mission, a Russian spacecraft carried a collection of tiny animals called tardigrades, also known affectionately as water bears, into the vacuum of space, where they were exposed not only to the absence of air and pressure, but also to the intense ultraviolet radiation and cosmic rays that pervade the environment beyond Earth's protective atmosphere. And after 10 days of this exposure, many of the tardigrades survived, reviving and resuming their normal activities once returned to hospitable conditions, demonstrating that life, at least in its most durable forms, can endure even the harshness of space itself. These discoveries have influenced scientific thinking about where life might be found beyond Earth and have informed a concept known as the galactic habitable zone, which was formally proposed by the astronomer Guillermo González in 2001. This concept extends the idea of a circumstellar habitable zone, the region around an individual star where conditions might be suitable for life, to the scale of the entire galaxy, asking which regions of the Milky Way are most likely to provide the conditions necessary for the emergence and long-term survival of living things. González and his colleagues suggested that the galactic habitable zone is an annular region, a ring-shaped area, located neither too close to the galactic center, where intense radiation and frequent gravitational disturbances from passing stars might sterilize developing life, nor too far out in the sparse outer reaches of the galaxy, where the relative scarcity of heavy elements might make the formation of rocky planets less likely. Our solar system, as it happens, sits comfortably within this proposed galactic habitable zone, in a relatively quiet neighborhood of the Milky Way where star density is modest enough to avoid frequent catastrophic encounters yet high enough to have provided the raw materials necessary for the formation of Earth and its sister planets. This positioning is sometimes cited as evidence that our location is somehow special, but it might equally be understood as evidence that habitable conditions are not rare at all, that a significant fraction of the galaxy's real estate falls within this favorable zone, and that we should therefore expect life to have many opportunities to arise throughout the spiral arms of the Milky Way, on countless worlds orbiting countless stars, each one a potential site for the slow and patient work of biological evolution. This brings us, inevitably and gently, to a question that has puzzled scientists and philosophers for decades, a question that was first articulated in its modern form by the physicist Enrico Fermi during a lunchtime conversation with colleagues at Los Alamos National Laboratory in 1950. Fermi, who was known for his ability to make quick and insightful calculations about complex problems, had been discussing the possibility of interstellar travel and the likelihood of extraterrestrial civilizations when he suddenly asked, with apparent genuine puzzlement, "Where is everybody?" This simple question, which has come to be known as the Fermi paradox, points to an apparent contradiction between the high probability estimates for the existence of extraterrestrial civilizations and the complete absence, at least so far, of any evidence for their existence, whether in the form of radio signals, visiting spacecraft, or any other detectable sign of intelligent activity beyond Earth. The Fermi paradox has generated an enormous literature of proposed solutions and explanations, ranging from the suggestion that technological civilizations inevitably destroy themselves before achieving interstellar travel, to the possibility that alien intelligences exist but have chosen not to make contact with us, to the more sobering hypothesis that we are simply among the first technological species to emerge in the galaxy, and that the silence we observe is the silence of a universe still waiting for its first long-distance conversations. Each of these explanations carries its own implications and its own emotional weight, and reasonable people can disagree about which is most likely to be true, but what remains clear is that the question itself, far from being a source of anxiety, is simply one more mystery in a universe that seems designed to inspire curiosity and wonder in those beings fortunate enough to contemplate it. And so, as we consider the Milky Way from the perspective of a traveler seeking to understand just how far one might journey before being truly alone, what we find is not a cold and empty void hostile to life, but rather a galaxy that seems, by its very structure and composition, to be quietly accommodating to the possibility of living things, a place where the ingredients for life are common, where suitable environments appear to be widespread, and where the processes that led to our own existence may well have occurred, independently and in parallel, on millions or even billions of other worlds scattered throughout the great spiral of stars. The galaxy, it seems, is not structured against life but rather seems to be quietly teeming with potential, a vast and patient nursery where the conditions for biology arise again and again, in star system after star system, across timescales that dwarf any human conception of history, and this realization, far from making us feel small or insignificant, might instead be received as a kind of cosmic reassurance, a gentle reminder that we are part of something much larger than ourselves, participants in a universe that seems, in its own quiet way, to be reaching toward complexity and awareness wherever the conditions allow. In the high desert country of Northern California, where the air runs thin and clear and the stars will overhead with a brightness that city dwellers rarely witness, there stands a collection of radio dishes arranged like flowers turned toward an invisible sun. This is the Allen Telescope Array, situated near the small community of Hat Creek, and since the year 2007 it has been listening. 42 dishes, each one 6 meters across, work together in a coordinated effort to catch the faintest electromagnetic whispers that might drift toward Earth from somewhere out in the vastness. The array was built through the combined efforts of the SETI Institute and the Radio Astronomy Laboratory at the University of California, Berkeley, and it represents one of humanity's most sustained attempts to answer a question that has lingered in our collective imagination for as long as we have looked up at the night sky and wondered whether anyone might be looking back. The dishes themselves are not particularly large when considered individually, but their power lies in their cooperation, in the way they pool their sensitivity to create a single instrument capable of surveying wide swaths of sky while simultaneously focusing on particular targets of interest. They sit there in the volcanic landscape, patient as stone, scanning the frequencies where a technological civilization might reasonably be expected to transmit, and they do so day after day, year after year, with a persistence that borders on the meditative. The mountains rise around them, pine forests climb the slopes, and hawks circle overhead in the thermal currents, and all the while the dishes track slowly across the heavens, gathering radio waves that began their journey long before any of us were born. This patient listening is not a new endeavor for our species, though our methods have grown considerably more sophisticated over the decades. One of the most intriguing moments in the history of this search occurred on August 15, 1977, when a man named Jerry Ehrman was reviewing data from Ohio State University's Big Ear radio telescope. The Big Ear was a fixed radio telescope, meaning it did not move to track objects but instead allowed the rotation of the Earth to carry different portions of the sky through its field of view, and on that particular summer evening it had recorded something unusual. A strong narrowband radio signal had appeared in the data, lasting for 72 seconds, which was precisely the duration one would expect for a signal passing through the Big Ear's observation window as the Earth turned. When Ehrman saw the printout, he circled the sequence of characters representing the signal's intensity and wrote a single word in the margin, expressing his astonishment at what the data seemed to show. That signal, which came to be known by the notation Ehrman had scribbled beside it, originated from the direction of the constellation Sagittarius, and it bore several of the hallmarks that researchers had long theorized a deliberate extraterrestrial transmission might possess. It was narrowband, meaning it occupied a very tight range of frequencies rather than spreading across the spectrum as natural phenomena tend to do, and it was strong, rising well above the background noise of the cosmos. Yet despite numerous attempts over the following decades, no one has ever detected the signal again. The Big Ear itself is gone now, demolished in 1998 to make way for a golf course, but the mystery of what it captured that August night remains. The signal could have been an artifact, a reflection of an Earth-based transmission bouncing off space debris, or it could have been something else entirely, and in the absence of a repeat detection, we simply do not know. It sits in the scientific record as a curiosity, a moment of unexplained strangeness in an otherwise quiet search, and researchers continue to wonder whether it represented a glimpse of something remarkable or merely a peculiar coincidence of natural processes we do not yet fully understand. The search has continued, growing more ambitious and more systematic as technology has advanced. In the year 2015, a Russian-Israeli entrepreneur named Yuri Milner announced an initiative called Breakthrough Listen, backed by $100 million in funding and designed to conduct the most comprehensive search for extraterrestrial intelligence ever attempted. The project secured observation time on some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, and it set out to survey 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies. The scale of the undertaking reflects both the technological capabilities we have developed and the recognition that the cosmos is vast beyond easy comprehension, that searching a meaningful fraction of it requires resources and dedication on a scale that previous efforts could not match. The data collected by Breakthrough Listen is made publicly available, allowing researchers around the world to participate in the analysis. And the project continues its work as you listen to these words, adding to the archive of observations that may one day yield an answer to the question that motivates the entire endeavor. Among the targets that have attracted particular attention in recent years is a star designated KIC 8462852, located approximately 1400 light-years from Earth in the direction of the constellation Cygnus. This star came to public notice through the work of Tabitha Boyajian, an astronomer who was examining data from the Kepler Space Telescope, which had been designed to detect planets by measuring the tiny dips in starlight that occur when a planet passes in front of its host star. Most such dips are regular and predictable, following the orbital period of the transiting planet. But the dimming events observed around this particular star were neither regular nor easily explained. The starlight dropped by as much as 22% on some occasions, far more than any planet could account for, and the pattern of dimming showed no clear periodicity, as if whatever was blocking the light did so according to no schedule that astronomers could discern. When Boyajian and her colleagues published their findings in 2015, the scientific community began proposing explanations, ranging from swarms of comets to dust clouds to irregular rings of debris. Among the more speculative suggestions was the possibility that the dimming might be caused by artificial structures, perhaps some form of megastructure constructed by an advanced civilization to harvest energy from their star. This hypothesis received considerable media attention, though most researchers considered it highly unlikely, preferring to seek natural explanations before entertaining more exotic possibilities. Subsequent observations have supported the idea that the dimming is caused by dust of varying particle sizes, perhaps the remnants of a shattered moon or the debris from planetary collisions. And while the star continues to exhibit unusual behavior, the consensus has shifted away from artificial explanations toward the conclusion that we are witnessing natural processes that simply happen to be more dramatic and irregular than most. Still, the episode illustrated how seriously the scientific community takes the possibility of detecting signs of technological activity, and how quickly attention can focus when observations deviate from expected patterns. Another class of signals that has captured scientific attention is the phenomenon known as fast radio bursts. Brief flashes of radio energy that last only milliseconds but release as much energy in that instant as the sun produces in days or weeks. The first of these bursts was detected in archival data from the Parkes Radio Telescope in Australia, recorded in 2001 but not identified until 2007, and since that initial discovery hundreds more have been catalogued. For many years, the origin of these bursts remained entirely mysterious, their brevity making them difficult to localize and their power suggesting processes of extraordinary violence or efficiency. Most appeared to occur only once, flashing into existence and then vanishing without repetition, which complicated efforts to study them in detail. Then, in 2012, researchers detected a burst designated FRB 121102, and in the years that followed this particular source was found to repeat, producing multiple bursts over time. This repeating nature allowed astronomers to train their instruments on the source more precisely, and eventually they succeeded in localizing it to a dwarf galaxy approximately 3 billion light-years from Earth. The distance was staggering, confirming that whatever produced these bursts was capable of generating truly enormous amounts of energy, and the association with a dwarf galaxy suggested the bursts might originate from a young and highly magnetized neutron star known as a magnetar. Subsequent detections have supported this interpretation, though the precise mechanisms remain an active area of research, and new fast radio bursts continue to be detected regularly, each one adding to our understanding of these powerful and enigmatic events. They are almost certainly natural in origin, products of extreme physics rather than technological activity, but they remind us that the universe contains phenomena we are only beginning to comprehend, processes that dwarf anything in human experience and speak to the tremendous energies that flow through the cosmos. In October of 2017, astronomers detected something unprecedented, an object passing through our solar system that had clearly originated from interstellar space. Designated 1I/2017 U1 and given the Hawaiian name meaning a messenger from afar arriving first, this visitor was small, perhaps a few hundred meters in its longest dimension, and it tumbled end over end as it swept past the sun and back out toward the stars. Its trajectory showed that it was not gravitationally bound to our sun, that it had entered the solar system from the direction of the constellation Lyra and would continue on its way into the darkness between stars, never to return. What made this object particularly intriguing was its shape and its motion. Observations suggested it was highly elongated, perhaps 10 times longer than it was wide, a geometry uncommon among known asteroids and comets, and careful tracking revealed that it was accelerating slightly as it moved away from the sun, as if something were giving it a gentle push. The most likely explanation for this acceleration is outgassing, the release of volatile materials from the object's surface as it warmed during its passage near the sun, producing a small but measurable thrust. This is the same process that creates the tails of comets, though in this case no visible tail or coma was detected, perhaps because the outgassing material was in a form that did not produce observable signatures. Some researchers, including the Harvard Astronomer AVI Lab, have suggested that the object's unusual characteristics might be consistent with an artificial origin, perhaps a piece of debris from another civilization, or even a deliberate probe sent to investigate stellar systems. This hypothesis remains controversial and is not widely accepted, as natural explanations appear sufficient to account for the observations. But the passage of this interstellar visitor reminded us that the space between stars is not entirely empty, that objects drift through the galaxy on timescales vastly longer than human history, and that we have only recently developed the ability to detect them at all. These varied signals and observations, from the unexplained radio burst of 1977 to the dishes of the Allen Telescope Array scanning the sky tonight, from the strange dimming of a distant star to the brief visit of an interstellar wanderer, collectively suggest something important about the universe in which we find ourselves. They suggest activity rather than emptiness, a cosmos that hums and flashes and whispers across frequencies we are only beginning to monitor with any sophistication. We have been listening in earnest for only a few decades, a span of time that is vanishingly small compared to the age of our galaxy, and our instruments, remarkable as they are, can detect only the tiniest fraction of what might be out there. The universe may be speaking to us in languages we do not yet recognize, through channels we have not thought to examine, in codes that will require generations more of patient study to decipher. For now, we continue to listen, pointing our dishes at the stars and recording the radio waves that wash over our planet every moment of every day. Most of what we capture is noise, the random electromagnetic hiss of natural processes, but buried somewhere in that noise there may be patterns, regularities, signals that carry meaning. The search requires patience, the kind of patience that comes naturally to the cosmos but less naturally to creatures whose lives are measured in decades. We have made a beginning, a serious and systematic attempt to hear what the universe might be trying to tell us, and whether or not we ever receive a clear message. The act of listening itself connects us to something larger than our own small concerns. The dishes turn, the data accumulates, and somewhere out in the darkness, the universe continues to whisper. When we imagine the space between stars, it is tempting to picture a vast and perfect emptiness, a darkness so complete that nothing at all exists within it. But this picture, as comforting as it might be in its simplicity, does not quite match what we have come to understand through careful observation and patient measurement. The space between the stars is not truly empty at all, but rather it is filled with an extraordinarily thin soup of matter and energy, a delicate web of connections that stretches across the entire galaxy and beyond, touching everything within it, including, of course, any traveler who might venture out into those seemingly lonely distances. This tenuous material that fills interstellar space has been given a name by astronomers, who call it the interstellar medium, and while this name might sound rather clinical or impersonal, the substance itself is anything but uninteresting. If you were to travel outward from Earth, leaving behind the comforting density of our atmosphere and the relative warmth of our planetary neighborhood, you would eventually find yourself surrounded by this gossamer-thin material, which consists primarily of hydrogen atoms drifting through the void at roughly 1 atom per cubic centimeter. Now, 1 atom per cubic centimeter might sound like almost nothing at all, and in truth it is an extraordinarily sparse concentration by any earthly standard, far more rarefied than the best vacuum we have ever managed to create in our laboratories. But across the immense distances of interstellar space, even this faint scattering of atoms adds up to something substantial, and you would never be entirely free of their gentle presence, no matter how far you might travel. Mixed in with these lonely hydrogen atoms, you would also encounter tiny grains of dust, particles so small that they would be invisible to the unaided eye, composed of silicates and carbon compounds and sometimes coated with thin layers of frozen water or ammonia or methane. These dust grains drift through the galaxy in numbers that are quite remarkable when you consider the scales involved, and they scatter and absorb the light of distant stars, which is why astronomers must sometimes peer through the darkness in infrared wavelengths to see what lies beyond these dusty veils. The dust is not distributed evenly, of course, but rather it tends to concentrate in certain regions, particularly along the plane of our galaxy, where it forms dark lanes and patches that can be seen even with modest telescopes on a clear night. And then there are the cosmic rays, which are not rays at all in the usual sense of the word, but rather particles, mostly protons and atomic nuclei, that have been accelerated to tremendous energies by violent cosmic events such as supernova explosions or the turbulent regions around black holes. These particles streak through the galaxy at speeds approaching that of light itself, and they permeate the interstellar medium in all directions, so that no matter where you might find yourself in the galaxy, you would be constantly bombarded by this gentle rain of high-energy particles. On Earth, we are somewhat protected from the most harmful of these particles by our planet's magnetic field and our thick blanket of atmosphere. But a traveler in deep space would be exposed to them more directly, and in a sense would be more intimately connected to the violent events that gave birth to them, even if those events occurred many thousands of light years away and many thousands of years in the past. It is worth pausing here to consider a rather remarkable idea that has been championed by certain scientists, an idea that suggests these connections between distant places in the galaxy might extend even to life itself. This idea is known as panspermia, from Greek words meaning seeds everywhere, and it proposes that the basic building blocks of life, or perhaps even dormant microorganisms themselves, might travel between star systems, carried along by comets or asteroids, or even drifting freely through the interstellar medium. The idea has a long history, but in more recent times it was explored with particular enthusiasm by two astronomers named Fred Hoyle and Chandra Wickramasinghe, who argued that the complex organic molecules necessary for life might have originated in interstellar space and been delivered to Earth and other planets by cometary impacts. While many of their specific claims remain controversial among scientists, the basic observation that organic chemistry is happening throughout the galaxy has been confirmed many times over, and it suggests that even in the loneliest reaches of space, the chemical precursors of life are present, drifting quietly between the stars. The evidence for this widespread cosmic chemistry includes some rather surprising discoveries. In the year 2000, astronomers studying a region near the center of our galaxy known as Sagittarius B2, which is a vast cloud of gas and dust where new stars are being born, detected the presence of a simple sugar called glycolaldehyde. Now, glycolaldehyde is not a particularly complex molecule by biological standards, consisting of just 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms arranged in a particular way, but it is nonetheless a building block that can participate in the formation of more complex sugars, including ribose, which forms part of the backbone of RNA, one of the fundamental molecules of life as we know it. The detection of glycolaldehyde in an interstellar cloud, floating freely in space some 26,000 light-years from Earth, was a gentle reminder that the chemistry of life is not confined to our small blue planet, but is instead part of a larger cosmic process that unfolds across the entire galaxy. And glycolaldehyde is just one of many organic molecules that have been found in interstellar space, joining a list that includes amino acids, the components of proteins, and various other compounds that would not seem out of place in a chemistry of life. Beyond the matter that fills interstellar space, there are also invisible threads of force that connect distant regions of the galaxy in ways that are not immediately obvious to our senses. The galaxy is permeated by magnetic fields, lines of force that thread their way between stars and through the interstellar medium, guiding the motion of charged particles and influencing the behavior of the gas and dust that surrounds them. These magnetic fields are not strong by everyday standards, typically millions of times weaker than the magnetic field of a simple refrigerator magnet, but they extend across such vast distances that their cumulative effects are quite significant. The Planck satellite, which was launched by the European Space Agency in 2009 and operated until 2013, made detailed measurements of these galactic magnetic fields by observing the way they affected the polarization of light from distant sources, and the maps it produced reveal a complex tapestry of magnetic structure that connects different parts of the galaxy in ways that are still being studied and understood. A traveler moving through interstellar space would be moving through these magnetic fields at all times, and while the fields themselves might not be directly perceptible, they would nonetheless represent a physical connection to the larger structure of the galaxy. There are also connections that pass through matter as if it were not there at all, ghostly particles that travel across the universe almost entirely undisturbed by the stuff they encounter along the way. These particles are called neutrinos, and they are produced in vast numbers by nuclear reactions, including the reactions that power the Sun. Neutrinos are extraordinarily reluctant to interact with ordinary matter, so reluctant that they can pass through the entire Earth as easily as light passes through a pane of glass. And they do so constantly, in numbers that beggar the imagination. At this very moment, as you lie quietly and listen to these words, trillions of neutrinos are passing through your body every second, most of them originating in the nuclear furnace at the heart of the Sun, and a few coming from more distant sources such as exploding stars or the cores of distant galaxies. These neutrinos carry information about the processes that created them, and in a sense they represent a continuous stream of messages from distant places, passing through you without your awareness but connecting you nonetheless to events occurring far away in space and time. In September of 2015, a new kind of connection was revealed to us for the first time, a connection that had been predicted by Albert Einstein exactly 1 century earlier but had never before been directly detected. On the 14th of that month, the 2 detectors of the Laser Interferometer Gravitational Wave Observatory, known as LIGO, one located in Louisiana and the other in Washington state, both recorded a faint signal that lasted for just a fraction of a second. This signal was the signature of gravitational waves, ripples in the fabric of space-time itself, which had been generated by a cataclysmic event that occurred roughly 1.3 billion light-years from Earth, the collision and merger of 2 black holes, each one roughly 30 times as massive as our Sun. The gravitational waves from this event had been traveling through space for over 1 billion years, spreading outward in all directions and growing weaker as they went, until finally they passed through the Earth and caused the mirrors in the LIGO detectors to shift by a distance smaller than the width of a proton. This detection was a profound achievement, not only because it confirmed a long-standing prediction of Einstein's theory of general relativity, but also because it revealed a new way in which distant cosmic events are connected to us here on Earth. Gravitational waves pass through matter just as easily as neutrinos do, perhaps even more so, and they carry information about the most violent events in the universe, information that is now accessible to us for the first time in human history. And finally, pervading all of space, filling every corner of the cosmos with its faint glow, there is the cosmic microwave background radiation, which is the oldest light in the universe, the faded remnant of the intense heat that filled the cosmos in its earliest moments. This radiation was discovered accidentally in 1965 by 2 radio astronomers named Arno Penzias and Robert Wilson, who were working at Bell Telephone Laboratories in New Jersey and trying to eliminate a persistent background noise from their antenna. No matter what they did, no matter which direction they pointed the antenna or how carefully they cleaned it, the noise persisted, a faint hiss coming equally from all parts of the sky. Eventually, after consulting with other scientists, they realized that what they were detecting was not noise at all, but rather the cooled-down remnant of the radiation that had filled the universe roughly 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. This radiation has been traveling through space ever since, cooling and stretching as the universe expanded. Until today, it has a temperature of just 2.7 degrees above absolute zero and peaks in the microwave portion of the spectrum. But it is still there, filling all of space. And no matter how far from Earth a traveler might venture, they would still be bathed in this ancient light, surrounded by photons that have been traveling since before the first stars were born, photons that represent a connection to the earliest moments of cosmic history. So the picture that emerges from all of this is one of profound and inescapable connection. Even in the deepest void between galaxies, where the density of matter drops to levels that are almost unimaginably sparse, a traveler would still be surrounded by the cosmic microwave background, still be touched by neutrinos streaming from distant stars, still be part of a universe in which gravitational waves carry information about distant events through the very fabric of spacetime itself. The interstellar medium, with its scattered atoms and dust grains and cosmic rays, would thin out considerably in intergalactic space, but it would never disappear entirely, and the organic molecules drifting through the cosmos would continue to drift, carrying their potential for chemistry and perhaps even for life. The threads of this invisible web may be gossamer thin, but they are everywhere, connecting everything to everything else in ways that are subtle but real. And so a human traveler, no matter how far they might journey from Earth, would remain a part of this interconnected cosmos, touched always by light and particles and ripples in spacetime that link them to the universe as a whole. And so we arrive, gently and without any great fanfare, at the place where our question finally finds its answer. And what a tender answer it turns out to be. One that perhaps you suspected all along as you listened to the distances grow and the familiar landmarks of Earth recede into memory. We asked how far a human being could travel from our small blue world before being truly alone, before finding themselves in some absolute emptiness where nothing accompanied them, where the universe had finally run out of companions to offer. We imagined, perhaps, that such a place must exist somewhere out there in the vastness, some boundary beyond which isolation would become total and the traveler would at last confront genuine solitude. But having wandered through all those light years together, having passed the planets and the stars and the galaxies and the great supervoids that stretch between the cosmic filaments, we find that no such boundary exists, and no such emptiness awaits. A human being could travel to the very edge of the observable universe, some 46 billion light-years from the place where you are lying now, and they would never, not for a single moment, be truly alone. This is the gentle truth that physics reveals when we follow its reasoning carefully and without drama, the kind of truth that does not announce itself with trumpets but simply waits to be noticed, patient and unhurried, like starlight that has been traveling for billions of years and does not mind waiting a few moments more to reach your eyes. At the farthest reaches of the observable universe, where the light arriving at our telescopes has been traveling since the cosmos was young and hot and strange, the traveler would still be bathed in the cosmic microwave background radiation, those ancient photons that have been journeying through space since the universe was approximately 380,000 years old. These photons fill all of space, gently and uniformly, a faint warmth of about 2.7 Kelvin that permeates every cubic centimeter of the cosmos. There is no escaping them, and no place so remote that they have not already arrived, because they were released everywhere at once when the universe first became transparent to light, and they have been everywhere ever since. Our hypothetical traveler, drifting at the edge of the observable universe, would be surrounded by these messengers from the beginning of time, cradled in the afterglow of the Big Bang itself, and the photons would carry no particular message except perhaps the simple fact of existence. The universe saying quietly that it is here and has been here and intends to continue being here for quite some time. And the photons would not be the only companions. Neutrinos, those ghostly particles that barely interact with matter at all, would be streaming through our traveler in their countless trillions, just as they stream through you now as you lie there listening to these words. Some of these neutrinos were born in the cores of ancient supernovae, those tremendous stellar explosions that scattered heavy elements across the galaxies billions of years ago. Others originated in the nuclear furnaces of stars that burned themselves out before our own sun had even begun to form. The neutrinos do not stop for anything. passing through planets and stars and human bodies alike as if they were made of nothing more substantial than a thought. And yet they are real. They are present. They are there with the traveler at every point along the journey. To be bathed in neutrinos is to be accompanied by messengers from the most energetic events in cosmic history, even if those messengers are too shy to introduce themselves properly. And then there is the matter of the traveler themselves. The atoms that compose their body and make up their bones and blood and the delicate architecture of their brain. Every one of those atoms, without exception, was forged inside a star that lived and died long before our own sun ignited. The hydrogen atoms are ancient, born in the first few minutes after the Big Bang when the universe was a hot, dense soup of elementary particles cooling rapidly into the first simple nuclei. But the heavier elements, the carbon that forms the backbone of every organic molecule in the body, the oxygen that fills the lungs, the calcium in the bones, the iron in the blood, all of these were manufactured in stellar cores under tremendous pressure and temperature, fused together through nuclear processes that we understand quite well and that operate according to the same physical laws everywhere in the universe. When those ancient stars exhausted their fuel and could no longer support themselves against their own gravity, they collapsed and exploded in supernovae, scattering their newly forged elements across the surrounding space, seeding the clouds of gas and dust that would eventually condense into new stars and new planets and, in at least one case that we know of, new living creatures capable of wondering where they came from. The astronomer Jill Tarter, who spent much of her career searching for signals from other intelligences in the cosmos, once reflected on this remarkable fact by noting that we are made of star stuff investigating the stars. This is not poetry dressed up as science, though it is certainly poetic, but rather a straightforward description of physical reality. The calcium in your bones was calcium in a stellar core. The iron carrying oxygen through your bloodstream was iron in the heart of a dying star. You are not merely observing the cosmos from some external vantage point. You are the cosmos observing itself. A temporary arrangement of ancient matter that has developed the curious ability to ask questions about its own origins. Our hypothetical traveler, then, 46 billion light-years from Earth, would carry this stellar heritage with them wherever they went. They could never escape it, because it is what they are made of. The loneliness we imagined waiting for them at the edge of the universe was based on a misunderstanding, a failure to recognize that the traveler and the universe are not separate things that might be brought together or pulled apart, but rather aspects of the same ongoing process, matter and energy flowing and transforming according to patterns that have been unfolding since the beginning of time. Let us take a moment to appreciate the scale of the structure through which this traveler would be moving. In 2016, a study led by the astronomer Christopher Cancellis, using data from the Hubble Space Telescope along with careful statistical analysis, estimated that the observable universe contains approximately 2 trillion galaxies. This number is larger than earlier estimates by roughly a factor of 10, and while future observations may refine it further, it gives us a sense of the sheer abundance of structure out there in the dark. 2 trillion galaxies, each containing billions or hundreds of billions of stars, each star potentially hosting planets of its own. The whole vast ensemble scattered across a volume of space so large that light itself needs billions of years to cross it. And these galaxies are not distributed randomly, like marbles dropped carelessly onto a floor, but are arranged in an intricate structure that cosmologists call the cosmic web. Picture, if you will, a spider's web on a cool morning, the silk thread strung between branches and catching the dew in small bright droplets. The galaxies of the universe cluster along filaments somewhat like this, long strands of matter connecting dense nodes where galaxy clusters gather, with great empty voids stretching between the filaments where matter is sparse and space is relatively quiet. This structure emerged from tiny fluctuations in the density of matter in the early universe, small variations that gravity amplified over billions of years, drawing matter together along certain paths and leaving other regions to expand into emptiness. The cosmic web is the skeleton of the universe, the underlying architecture on which everything else is hung, and wherever our traveler went, they would be moving through this web, following filaments or crossing voids, but always within a structure that connects them to everything else. And speaking of travelers, let us return for a moment to one who is actually out there right now, drifting through interstellar space at this very moment, carrying a little piece of Earth with it. Voyager 1, launched in 1977, has now traveled farther from the Sun than any other human-made object, and it crossed into interstellar space in 2012, leaving behind the bubble of solar wind that surrounds our star and entering the space between the stars. As of today, Voyager 1 is more than 24 billion kilometers from the Sun, and it is still sending signals home, faint radio whispers that take nearly a day to reach the receiving dishes on Earth. The spacecraft carries a golden record, a kind of message in a bottle, containing sounds and images selected to represent our planet and its inhabitants, greetings in dozens of languages, music from many cultures, the sound of a human heartbeat, the call of a humpback whale. Voyager 1 will never reach another star in any human timescale, and the signals it sends will eventually fade below the threshold of detection as its power source dwindles. But the spacecraft itself will continue drifting through the galaxy for millions of years, perhaps billions, a small artifact carrying human voices into the dark. It is not lonely, exactly, because loneliness implies the capacity to feel alone, and Voyager is simply matter moving through space according to the laws of physics, indifferent to questions of companionship. But we can take comfort in knowing that it is out there, that something we made and something that carries our voices is moving through the interstellar medium, surrounded by the same photons and neutrinos and cosmic rays that would accompany any human traveler who followed in its path. The loneliness we imagined at the beginning of our journey, the terrifying isolation that science fiction often places at the heart of space travel, turns out to have been an illusion, a projection of very human fears onto a cosmos that does not share them. We are not separate from the universe in any meaningful sense. The boundaries we draw around ourselves, the skin that separates our bodies from the air, the walls that separate our homes from the night, these are useful distinctions for navigating everyday life, but they do not represent any fundamental discontinuity in the fabric of reality. The atoms in your body are exchanged constantly with the environment. The air you breathe was once inside other lungs. The water you drink has cycled through countless living things over billions of years. There is no hard edge where you stop and the universe begins. And so as you lie there now, perhaps feeling the gentle weight of blankets, perhaps hearing the small sounds of the night, you can rest in the knowledge that you are held by the same forces that hold the galaxies in their web, woven from the same matter that forms the stars, bathed in the same light that has been traveling through space since before the Earth existed. 46 billion light-years is a very long way, farther than any human being will travel in any foreseeable future, but even at that distance, you would not be alone. The universe does not abandon its components. The photons would still be there. The neutrinos would still pass through you. The atoms of your body would still carry the memory of stellar fires long extinguished. You are star stuff, As the scientists remind us, and star stuff does not get lonely in the way we feared, because it is always and everywhere part of the larger whole. The void between galaxies is not empty but full of fields and particles and the lingering echoes of cosmic history. The darkness between stars is crossed by light we cannot see. The silence of space is not really silence at all, but a quietness filled with signals too faint or too strange for our ordinary senses to detect. Let yourself drift now, carried on the gentle current of these thoughts, knowing that the question we asked has found its peaceful answer. You could travel as far as the universe permits, to the very edge of the light that has had time to reach us since the beginning, and you would still be accompanied, still connected, still held in the vast and gentle embrace of everything that exists. This is not a lonely cosmos after all, only a very large one, and you are part of it, now and always, made of the same ancient light,